Welcome to the hardware design and development demo session. A little bit of background about me. I have 25 plus years of experience in areas like R&D, production, marketing, sales, management, in various industry domains, including biomedical systems, semiconductors, and transportation. And also for close to a year now. Here is the course curriculum. The course curriculum includes many topics. That includes the basics, the hardware design development process, how it is going to. That is this session, and then about the basics like active elements, passive elements, op amplifiers, logic gates, flip flops, and it has sessions that cover power supplies and the methods in the power supplies, the technique of the power supplies, and it also has some more basic on push-pull kind of port pins, GPIO pins, memory interfacing technologies, and interfaces with various peripherals like RS485, RS430, RTC, SPI, I2C kind of peripheral interfaces. Also interfacing with wireless module like Wi-Fi module, Bluetooth, ZigBee, all the CPRS, Edge modules. Also how to interface switches, relays, and things. Also about PCB fabrication and the mechanical designs, mechanical based designs, and the CAD system, for the CAD. Also how basically in a automatic production plant, how does the what kind of machines are used, how these machines are used. Those are also covered. And also layout rules, basically the design rules, basically checks, and the DRC design rule checks. Those are also covered. Now, today's agenda, we're basically going to talk about hardware design flow. What happens in hardware design flow during the hardware design? What are the things that are considered and how basically the entire flow actually goes, product design. And a little bit about this course before we start, we can also talk about it. It's basically, this is an intermediate level course, and it basically talks about hardware design and microcontroller based, particularly microcontroller based designs. And it focuses more on digital design because there is some analog design, power supply designs, and also covered as seen in the curriculum. But the more focus is basically on digital design. Focus is there on hands-on design. There is a schematic capture tool is basically recommended and is used in the training. Basically, the schematics capture is basically start. Focus on the circuit design of the hardware, definitely going to be there. How the components are selected, how they basically are connected, what are the interfaces, the signaling, the purpose of each of the signals, and how the timings of the signals. Those are the in a circuit design basically covered. Course time does not involve fabrication due to the online nature of it. We don't really fabricate the hardware. Similarly, the layout drawings is also not part of the course. We don't discuss the layout drawings in extent. Some amount of layout is basically discussed and the precautions what to take care of in the layout and that. Because we don't use the layout tool, but then we basically recommend the auto layout option. Prerequisites for this course is basically somebody should have some digital electronics, analog electronics, and circuit theory. Digital electronics, basically one need to understand typically the definitions, gates, flip flops, counters, timers, registers, microcontrollers. These things if one understands, that is fairly good enough. And analog electronics like oscillators, ADC, DAC, timers, multivibrators, voltage dividers. Of course, there is basically sections on ADC and DAC, the more advanced ADC and DAC, but one should understand what an ADC is. Similarly, circuit theory, if one understands Ohm's law, Kirchhoff's law, transmission line theory, these are some of the prerequisites that we expect the participants to have. Now, let's look at the hardware design of the product development, hardware product development life cycle. It is typically, involves developing a block diagram and circuit design, basically schematic capture and layout drawing, then order the PCBs and components and then populate the PCB, then PCB testing, firmware writing firmware and the microcontroller, using the firmware into the microcontroller and testing the product. This is a usual product engineering, hardware product engineering. In that, basically hardware design, primarily intensity the design really happens at the circuit design stage and the block diagram circuit. One may have a question as to is it analog design or a digital design? What is basically the answer to that question is basically product design includes both analog and digital design. But what we hear basically in the scope mainly primarily focus on system integration of digital components and design with digital components. Almost there is some analog design that's been discussed about the plate design and all that, but basically microcontroller based designs that we are looking at go in detail. A modern day product involves digital design and involves that is basically now a variety of hardware basically can be thought of such as the industrial electronics, mobile electronics, control, medical electronics, communication and different electronics. These are all there, and then there is also variety of form factors that we see in the wearable, handheld devices, benchtop, wall mount. The question that would come, so of course, does it specify in any of them or is it generic? It is essentially a generic in nature. Whatever is taught is applicable across all these industries and all these different types of hardware. But you can see there's basically developing a single PCB, of whatever the form factor is, a single PCB including microcontroller hardware. Design, when we're talking about basically hardware design, the hardware design involves several steps. It includes selecting the peripheral, basically identifying what peripherals the hardware design. The block diagram stage, you basically try and understand what peripherals that it needs. Does my hardware need a USB interface? Does it need an Ethernet interface? Does it need any of the legacy RS-232 or 485? So one would basically identify the peripherals that are needed. And then once the peripherals are identified, a processor is selected. That the processor selection basically includes selecting a processor that will support these peripherals. And the processor selection is involved process, and there is a session that how to go. The design criteria that are required that are basically to be considered in selecting the process. Peripheral chips selection. So the peripherals are identified. So every peripheral gets interfaced to the processor through a peripheral chip. Basically, a peripheral chip selection is done, identifying the right physical layer chip or a level chip or one of the peripheral interfacing ICs is selected. So the selection of the peripheral chips happens. Then one goes about identifying the interface that the peripheral chip should have and study the interface. What does the interface between the peripheral chip and the is it a proprietary interface or is it basically an I2C kind of interface? One needs to study what is the interface, what speeds it runs at, what signals it has, and what is the significance of each of the signals. So that the things that one would do in what kind of power supply that needs. So these are the interface. Once that happens, the interface design is completed. The processor and the peripheral chips are all connected. Then goes the power supply. One needs to design a power supply basically to cater to the power supply needs of every one of the chips on the board. And similarly, also the boot design and JTAG design are also need to be paid attention. They are not major part of a design, so to say, they are not a major design elements, but they are crucial elements, so one has to basically pay attention. The bootstrapping of the boot pin doesn't properly happen, code doesn't start from right position, so one need to pay attention to the boot. And similarly, the JTAG is an important aspect of modern control design. We'll see shortly about it, and that's basically need to be and then basically listing all the layout precautions, what are the peripherals that are used and what kind of precautions that need to be taken in connecting the peripherals and routing the signals and all. So the layout precautions are in terms of the ground and the power planes and all are basically. A typical system diagram looks a block diagram looks like this with a microcontroller at the center of the main brain of the entire computing element, and that may require additional SRAM and flash outside the microcontroller. Typical microcontroller has inbuilt SRAM and flash, and but some designs may need additional SRAM and flash. They will be interfaced to the microcontroller. Keypad, LCD, USB, Ethernet, these kind of interfaces, RS-232, 484, and then wireless connectivity module. Any sensors are there that are basically used. They connected to I2C or SPI kind of interfaces. And a power supply design is also basically is part of the board that basically supplies power to all these different elements of the microcontroller. Now, processor selection, like you said, process selection is a part of the design process. And there are so many companies to choose a processor from. Motorola, Analog Devices, Texas Instruments, Estimator, Renesas, Marvel, you name it. There are so many of these companies, around 20 to 30 manufacturers are there that make processors. They make processors of 8-bit, 16-bit, 32-bit. The processors are basically come in, either VGA package, LPFP, bit package, and RISC and CISC and ARM-based designs are there. And processors may run at different speeds, that is, different clock speeds, 30 megahertz at 120, and different speeds, high speeds, 800 megahertz. So how do you select a processor that is basically suits the application? How do you know what is the speed that is necessary for the application? What are the interfaces that microprocessor needs? So it is selecting a processor is like buying a car with so many features and bells and whistles that it has. So it is always a trade-off between different things and all. Selecting the processor, there is a session based on for processor selection. Once a processor is selected, one need to read the data sheets of the processor, block diagram, the data sheets, read it in phase-wise, understand the data sheet, and also not only the data sheet, one may also have to refer to the reference manual of the SoC. The reference manual may be mostly read by the software engineer, firmware engineer, but also sometimes the hardware engineer may also need to look at the reference manual in order to understand what are the speeds that the interface speeds that the processor supports and all. So that data sheet reading is an important aspect of the design. Not only the data sheets of the microcontroller, but the data sheet of the peripheral chips and all. Typically, a peripheral chip is interface. This is an SoC, and this is the connector of the Ethernet connector, including the magnetics and that. And there is a peripheral chip called Ethernet 5 that basically connects the connector to the SoC, and it has an interface here. One need to understand what are the signals that are present here in this interface and what is the significance of each of the signal, timing of those signals, and the power level or the voltage levels of those signals. Similarly, on this end to the SoC, what is the interface? Is it a standard interface? What is the standard? What is standardizing that? What are the signals again? Their timing and then the voltage levels and all that one need to understand. And then basically make this interface design. Similarly, you are designing an RS-232 based board and then a DB9 connector, that's the typical connector that goes serial port connector, and that is connected to a level shifter RS-232 to the driver level shifter and connects to the SoC. So one need to understand how this interfacing happens. So that way, not only for these two interfaces, but many interfaces, you design and learn and design the interfaces. Power supply design. Power supply shall be able to support all the voltages in the board. The board may have 1.2 volts, 1.8 volts, 2.5, 3.2. Different voltages may be present in the board in order for the both the IOs as well as the core as well as different level of IOs to properly function. So the power supply design should take care of generating each of these power supply rail, and every power supply rail, it has to be sufficient current into supply. If sufficient current is not supplied to the chips don't function correctly, they malfunction and the intended function does not happen. You need to look at that. Not only the power supply, the current from mains. If it is a battery based, one has the power supply design should include the battery based design. What happens in battery based design? How does the battery charge the power supply? How does the battery when it is operating when the device is operating standalone, how it would basically operate from the battery. These are the things. Also, in several industries where safety is important, such as transportation or defense, space electronics, and carrier, basically medical electronics. Basically, one need to provide isolation between high voltage and low voltage power supplies. So those kind of isolations need to be provided in the power supply. As we discussed, board design is an important crucial aspect of it. Typically, the microcontroller has 4 pins. The 4 pins basically need to be properly bootstrapped when the processor is turning on, is basically powered up. So the board design becomes crucial for board working. The curriculum will dwell into handling the 4 pins of the processor and powering up the processor. JTAG design, basically the JTAG port is a special port that modern SoCs basically contain and help in choosing code into internal memory as well as debugging the program and the troubleshooting of the hardware. So modern hardware design shall take care of proper JTAG design that involves connecting JTAG microcontroller to proper pins of the in-circuit emulator. So the any in-circuit emulator is typically connected to the JTAG port, and then through the in-circuit emulator, one would download the program and all that. So this JTAG design is important aspects of the microcontroller design. And then as we discussed interfaces, basically peripheral chips are connected to the microcontroller interfaces. Understanding and design proper interfaces with the peripheral chips is key to the success of hardware design. A particular kind of peripheral may be available with I2C, SPI, or UART. So there are design choices. The design choices vary, and one would basically go about selecting one of the interfaces for the peripheral chip. If you're using a sensor, whether you select an I2C interface or an SPIC, it's a design choice and a design concept. Typically, in this, the tools that are used are basically a schematic capture tool. And for the block diagram, either PPT, Word, or a kind of tool basically can be used. So we recommend the participants to have a tool, a schematic capture tool, like an arcade, Altium design maker, circuit maker, one of these. Some of these tools are free to, or you can probably obtain a evaluation license of the tool and then basically use that in the course. What is schematic capture? A schematic capture is basically once all the key chips are identified and selected, design is captured into a schematic that runs into several pages. In each page, the schematic capture tool, you use basically one of these arcade capture tool or Altium capture, and then you place the chip in one of the page, and then interconnect the chip with the other chips in other pages at the same page, connect them with the traces. The traces are typically called nets. So you'll be basically connect with traces, connect the power supplies, connect the connectors and whatnot, everything that basically logically need to be connected in the schematics is basically created. Schematic is logical. It does not specify how the physical connection on the PCB are. It does not show where the connection is going to reside on the PCB, where exactly on the PCB is created. That is typically done in the PCB Layout Tool, and the PCB Layout Tools will have facility to import the schematics. The schematics that are created during the design process, those schematics are imported into the layout, and the layout basically specifies layout tool, you specify how many layers of the PCB you are making and import all the connections into the PCB layout tool. The PCB layout tool by default basically creates the netlist onto the PCBs into several layers, and you can change the track width, the connector placement, location, holes and all the mounting holes, those things you can define. So this is where you actual physical PCB is created. It does not include the PCB thickness, trace height, trace material, what type of PCB material you use and all that. They are typically sent as instructions to the PCB manufacturer. So that's how basically the design process goes. Then once the PCB comes from the fabrication unit, you would basically populate the PCB and go through the rest of the testing, the firmware writing. Now this course, how do you follow this course? You basically follow the presentation, ask questions, gather resources like data sheets and all that are necessary. Some videos, additional videos are also recommended that one can watch to gather those, right? Read the data sheets, watch those videos, and draw the schematics on a daily basis. Whatever you start in this session, draw those schematics basically on your own. In the session, basically the schematics are shown, but one has to do it on their own, draw the schematics. Ask questions in the next question, anything on the schematic. Submit the schematics in PDF format so that I can review them and comment as to what can be better, what is good, and what is to be improved, and all those kind of suggestions can be given. Now, this course technology. In today's market, basically, board-level hardware design is in demand in semiconductor companies, automobile companies, and many industries that have systems. This hardware design is basically used in verification of semiconductor in semiconductor industry. Let's say if it's a processor company or some kind of peripheral chip company, they need to test those peripherals, really put it onto it. So the verification also involves not only VLSI verification but also board-level that will involve this kind of verification towards board level design. That's where a board level design is done. Hardware design is done in companies that develop physical products for specific industry requirements, such as the industrial automation, railways, telecom, space and defense. In these areas, basically, we need to create hardware. The hardware design basically done by hardware design engineers that need to understand these kind of things. Certifications will provide a verifiable course completion certificate at the end of the course. Once the course is completed, you will be given a course completion certificate that can serve in your career development, that will serve a great deal of help in your career. Additional course resources, basically the course resources are provided during the time of the related topic is covered. The data sheets and those kind of things are basically explained. The data sheets basically recommended to download on your own. That way, navigate how to navigate through the semiconductor manufacturing website and download it. If there are difficulties, but I would definitely cover those data sheets. The recordings of all the design lectures will also be shared with the students and all. So any doubts regarding the subject discussed here in the hardware design flow? Any questions regarding course timings, resource location? Those things can be discussed with course timings and resource locations that can be discuss with the person that is you are in contact with. But I can take any questions that are there on the questionnaire now. Thank you for your participation.